Hello everyone. Today we will going to see some practice questions from the chapter Organic Compounds Containing Oxygen. This is part 3. Let's start. Disclaimer. The images used in our slide deck are for educational purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. Practice questions from 21 to 30. So we will see some practice questions. Let's start with our first question. An ether A C5H12O, when heated with excess of hot concentrated HI, produced two alkyl halides, which, when treated with NaOH, yielded compounds B and C. So we have given a proper reaction that ether C5H12O having molecular formula. When it is heated with excess of hot concentrated hydrogen iodide, it will produce two alkyl halides, which, when treated with NaOH, yielded two compounds named B and C. Oxidation of B and C gave a propanol and an ethanoic acid respectively. So when you oxidized the B compound obtained, it will give propanol, and when you oxidize C compound, it will give a ethanoic acid. The IUPAC name of ether A is, so the ether A which is given as C5H12O, we have to find out the IUPAC name of ether. This question has been in JEE Mains in online mode in 2030. Options are 2-ethoxypropane, ethoxypropane, methoxybutane, or 2-methoxybutane. You have some time to think about this question. After that, we will see the answer. Okay, let's see. The correct answer for the given question is option A, that is 2-ethoxypropane. Ether A, which we have to find out, is 2-ethoxypropane. You can see we have our A compound, which is a ether, and name is, the IUPAC name is 2-ethoxypropane, because in the main chain we have 3 number of carbons, and at the second position we have ethoxy group. That means ethyl and oxygen, right? So its name is 2-ethoxypropane. And as the question says that when you react the ether A with the hydrogen iodide, it will give you alkyl halides like C3H7I and C2H5I, which, when treated with NaOH, yielded compounds B and C. So when you react this alkyl halide with NaOH, you will have a compound named B, which is CH3CHOH CH3. So it will be propanol. And when you react C2H5I alkyl halide with NaOH, you will get C2H5OH ethanol, which is a product C, right? And when you oxidize these two, the oxidation of B yielded propanol, and the oxidation of C yield ethanoic acid. Okay, as per the question said, so it is satisfying all the conditions as per the question. So that is why we have our ether, which is 2-ethoxypropane. Propane. So our correct answer is option A, that is 2-ethoxypropane. Let's move on to our next question. Phenol on treatment with CO2 in the presence of NaOH followed by acidification produces compound X as the major product. So when you react phenol with the CO2 carbon dioxide in the presence of sodium hydroxide and then you do acidification, you will get a compound X as a major product. Now, when you treat X on treatment with CH3CO whole twice O in the presence of catalytic amount of H2SO4, what will you get? What it will be producing? This question has been in JEE Mains in 2018. Options are the benzene ring having COOH and COOCH3 as a side chains, or benzene ring having COH and COOCH3 as a side chain on para positions, benzene ring having OH and COOCOCH3 as a side chain at ortho and para position respectively, or benzene ring having COOH as para positions and COH at meta position and COOCH3 at alternative para position. So you have these four options. You have to select the one product which you will get when you treat the X with CH3CO whole twice O in the presence of catalytic amount of H2SO4. You have some time to think about this question. After that, we will see the answer. Let's see. The correct answer for the given question is option A. So this is the phenol. When you react it with CO2 and NaOH and you do acidification, you will get a product X. And when you react X with CH3CO whole twice O in the presence of catalytic amount of concentrated H2SO4, what will you get? This is the question. The very first reaction in the above roadmap looks like col-base reaction. So this first reaction is looking like a col-base reaction, which results to salicylic acid. So when phenol reacts with CO2 and NaOH, and when you do that acidification of that, you will get a product named salicylic acid. This is a col-base name reaction. Okay, salicylic acid, benzene having OH and COH group at para and meta positions respectively. So this is compound X. The salicylic acid with acetic anhydride CH3CO whole twice O in the presence of catalytic amount of concentrated H2SO4 undergoes acylation to produce aspirin. As this salicylic acid you get after reacting phenol with CO2 and NaOH, and then you are reacting it with acetic anhydride CH3CO whole twice O. Now what will happen? This is an acidic hydrogen in the OH, so it will be released. So H positive will be released from here, and O negative will remain at as it is. And acetic anhydride, from acetic anhydride you will get CH3CO negative, CH3CO positive. Now the CH3CO negative will attack on this H positive, or you can say H positive attack on the CH3CO negative, and you will get CH3COH, that is ethanoic acid, and rest of the ion, which is CH3CO positive, will get attached to the oxygen having the negative charge on the benzene. So you will get acetyl salicylic acid, that is benzene having COOH at the meta position and OCOOCH3 at the ortho position. Name is acetyl salicylic acid, that is aspirin, and ethanoic acid as a side product. Aspirin, which you will get as a final product, is a non-narcotic analgesic, that is a painkiller. It is used as a painkiller. Let's move on to our next question. PHOCOPH. Given compound can be prepared by the reaction of. So this is a let's suppose this compound, you have to find out the formation of this. Okay. So what you will do? How can you prepare that? This is our question. Options are phenol and benzoic acid in the presence of NaOH, phenol and benzoyl chloride in the presence of pyridine, phenol and benzoyl chloride in the presence of zinc chloride, or phenol and benzaldehyde in the presence of palladium. You have some time to think about this question. After that, we will see the answer. Let's see. The correct answer for the given question is option B, that is phenol and benzoyl chloride in the presence of pyridine. For the reaction of this compound given, following reaction takes place. Phenol will react with benzoyl chloride, that is PHCOCl, in the presence of pyridine, and you will get your desired product, which is benzene ring attaching with two benzene rings together attached with the COO bond. Okay, so you will get the main product which you want to find out, which you want to prepare, plus HCl as a side product. So this is the reaction followed for the preparation of the given compound in the question, and that is why we have our correct answer as option B, that is phenol and benzoyl chloride in the presence of pyridine. You can do this reaction for the preparation of the given compound. Let's move on to our next question. Which is the suitable catalyst for bringing out the transformation given below? So we have given a transformation, you can say, reaction, you can say, in which a cyclohexane ring directly cut and attached to the double bond O, like this is a carbonyl ring, you can say, okay, and plus SHCH2 CH2SH, and they are reacting together and forming this compound, which is a chain, which is a ring compound. Okay, you have to find out a suitable catalyst for this transformation given. Options are BF3 and ethyl oxide, NaO ethyl, tungsten lamp, or diabenzoyl peroxide. You have some time to think about this question. After that, we will see the answer. Okay, let's see. So the correct answer for the given question is option A, that is BF3 and diethyl oxide. So BF3 increases the electrophilicity of the carbonyl carbon. That is this carbon attaching to double bond O. This is a carbonyl carbon. Okay. So what BF3 will do, we will take it as a catalyst, and what will it will do? It will increase the electrophilicity of carbonyl carbon, and BF3 will act as a Lewis acid, due to which sulfur attacks on the carbonyl carbon and form the direct bond between the carbon and the sulfur. Okay, and form this ring compound, in which you can see we have a cyclohexane from at which one carbon is connected to the two sulfurs and CH2CH2. The ring is forming. Okay, so we use BF3, which will increase the electrophilicity of this carbonyl compound, carbonyl carbon, so that sulfur can easily be attacked on the carbon, right? And thus we have our correct answer as option A, that is BF3 and diethyl oxide. Okay, let's move on to our next question. Which compound would give 5-keto 2-methyl hexanal upon ozonolysis? From the options, you have to select one compound which will give this product, that is 5-keto 2-methyl hexanal, when you do its ozonolysis, and you treat it with ozone. This question has been in JEE Mains 2015. Options are, you have cyclopentane ring, where two methyl groups are attached at the first and the second position. Again, or you have cyclopentane ring, where the two methyl groups are attached at the first and the third position. Or same cyclopentane ring, two methyls are attached at the first and the fourth position. And lastly, same cyclopentane ring and the methyl group are attached at the first and the fifth position. You have to select one compound which will give 5-keto 2-methyl hexanal upon ozonolysis. You have some time to think about this question. After that, we will see the answer. Let's see. The correct answer for the given question is option B, that is a cyclopentene ring having two methyl groups at first and third position. So, as you have given in the option first, a cyclopentene ring having first and second position attached with the methyl groups. When you do the ozone of this in the presence of zinc and H2O2, you will get heptane 2,6 diaketone. Okay, so what will happen? This double bond will break. So you will get CH3 and this carbon uh, between which two carbons between which double bond is forming. So double bond O will come on this carbon. Okay, so the formula will you will get is CH3 C double bond O CH2 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 C double bond O CH. Okay, and name, if you name it, it will be heptane 2,6 diaketone. Okay, but in the question you have asked about 5-keto 2-methyl hexanal. So let's see for the option B. In the option B, you have cyclopentene ring, methyl at the first and the third position. Again, you do the ozonylysis, heat it in the presence of zinc and hydrogen peroxide. This time you will get 5-keto 2-methyl hexanal. That means ketone and aldehyde group in the same chain. So basically, again, this double bond between these two carbons, so they will break. And as at the first carbon CH3 is attached, so at the first carbon double bond O, that is ketone group will attached. CH3 C double bond O CH2 CH2 CH, at which CH3 is a side chain, and then again C, but double bond have been broken up. So this C will attach with the oxygen and hydrogen is already present, so it will form CH2 aldehyde. Okay, and that is how ketone and the aldehyde group both will be present in the same product. So what you will get? You will get 5-keto 2-methyl hexanal. Okay, we have asked about this, and that is why the compound which should be giving 5-keto 2-methyl hexanal after ozonylysis is present in the option B. While in the option C, you have the structure cyclopentene ring having methyl side chains at the first and fourth position. You do the ozonylysis for this, you will get 5-keto 3-methyl hexanal ketone and the aldehyde group. Why? Because the double bond between two carbons, right? But CH3 is not attached to these two. The position of CH3 is changed. So at one of the carbon between which double bond is present, at one of the carbon aldehyde group will go, and at one of the carbon ketone group will go. Okay, ketone group will go at the carbon where CH3 as a side chain is present, as a side group is present. Okay, so you will get CH3CO, CH2 CH3 CH2 CH2. And as per the structure given in option D, which is cyclopentene having CH3 at the adjacent carbons but not at the double bonded carbons, you will do ozonylysis for this and you will get 5-keto 4-methyl hexanal, which is CH3 C double bond O, because of course the one carbon which is involved in the double bond and having side chain as a side ring as a CH3 methyl group, so it will attach to the ketone group. So C double bond O, then CH, CH3, and then CH2, CH2, and then CH2, and then CHO. Okay. So you will get 5-keto 4-methyl hexanal. Okay. So the correct answer is option B as per the given question. Let's move on to the next question. The most suitable reagent for the conversion of RCH2OH to RCHO is, that means alcohol to aldehyde. If you want to convert a primary alcohol to the primary aldehyde, what will you do? What suitable reagent you will use? This question has been in JEE Mains 2014. Options are KMnO4, K2Cr2O7, CrO3, or PCC, pyridinium chlorochromate. You have some time to think about this question. After that, we will see the answer. Okay, let's see. The correct answer for the given question is option D, that is PCC, yani pyridinium chlorochromate. So you have to convert RCH2OH into the RCHO, C double bond OH. But you have to use PCC for this. Pyridinium chlorochromate, PCC, is the mild oxidizing agent which causes conversion of alcohol to the aldehyde stage. So PCC is basically mild oxidizing agent which can convert alcohol to the aldehyde stage, while all the others reagent cause the conversion of alcohol to direct acid. So they are a strong oxidizing agent, so they directly convert alcohol to the acid after the oxidation of the alcohol. But meanwhile, PCC, pyridinium chlorochromate, is a mild oxidizing agent. It will oxidize alcohol to the aldehyde stage. And that is why we use PCC for the conversion of alcohol to aldehyde. And thus we have our correct answer as option D. Let's move on to our next question. In Rosenman reaction, RCOCl plus hydrogen at the presence of palladium and BaSO4, RCHO you will get plus HCl as a side product. BaSO4 here. So what is the function of BaSO4 you have to tell. Options are promotes catalytic activity of palladium, removes the hydrogen chloride formed in the reaction, deactivates palladium, activates palladium. You have some time to think about this question. After that, we will see the answer. Okay, let's see. The correct answer for the given question is option C, that is deactivates palladium. So BaSO4 decreases the activity of palladium. When you are using palladium and BaSO4 in this conversion from RCOCl plus H2 to RCHO plus HCl, so what BaSO4 will do, it will decrease the activity of palladium present as a catalyst in this reaction, this conversion. RCOCl plus H2, palladium or BaSO4, RCHO plus HCl you will get. Okay. So here the role of BaSO4 is to decrease the activity of palladium as a catalyst. And thus we have our correct answer as option C, that is deactivates palladium. Let's move on to our next question. The formation of aldehyde from alkyl cyanide is related with the name. So you have asked about a reaction that when you form the aldehyde from alkyl cyanide, what this conversion is called. What is the name of this relation? Options are Stephan reaction, Rosenman reaction, Woods reaction, or HVZ reaction. You have some time to think about this question. After that, we will see the answer. See, the correct answer for the given question is option A, that is Stephan reaction. Formation of aldehyde from alkyl cyanide takes place by Stephan's reaction, which is a name reaction. So alkyl cyanide RCN plus 2H in the presence of SnCl2 and HCl, you will get aminochloride RCH double bond NH dot HCl, which when you react with H2, it will give you aldehyde plus NH4Cl ammonium chloride plus water molecule. Okay, so you will get a aldehyde from alkyl cyanide. This reaction is a name reaction and it is called Stephen's reaction. That's why we have our correct answer as option A, that is Stephen reaction. Let's move on to our next question. The product of acid hydrolysis of P and Q can be distinguished by. We have given P, which is CH2 double bond C, TH3, OCOCH3, and Q, which is CH3, CH double bond CH, OCOCH3, Q. So, we have asked that what will be the product of acid hydrolysis of P and Q? Or you can say that the product of acid hydrolysis of P and Q can be distinguished by which test? Options are Lucas reagent, 2,4-DNP, Fehling solution, or NaHSO3. You have some time to think about this question. After that, we will see the answer. Okay, let's see. So the correct answer for the given question is option C, that is Fehling solution. So this is P, that is CH2 double bond C, OCOCH3 and CH3. When you acid hydrolyze it, you will get enol form, which is CH2 double bond C, OHCH3 plus CH3COH as a side product. And this enol form undergoes tautomerization and it will convert to acetone, which is a keto form. So acetone CH3COCH3. So enol form, from the enol form, after the tautomerization, you will get acetone. Okay. Fehling solution is not reduced with acetone. So basically, acetone, from the acetone, you will get acetone, right? So from acetone is not reduced, or you can say Fehling solution is not reduced with the acetone you get from the P. While this is Q, which is CH3, CH, double bond CH, O, C, O, CH3, you will do acidification. You will get enol form, which is CH3, CH double bond CHOH plus CH3COH as a side product. When you do tautomerization of this enol form, you will get a aldehyde, which is CH3CH2CHO. Fehling solution is reduced with aldehyde. So, Fehling solution is reduced with the aldehyde you get after the acid hydrolysis of the Q product. Okay. Hence, the product of acid hydrolysis of P, which is ketone, and Q, which is aldehyde, can be distinguished by the Fehling solution, as Fehling solution is reduced by the aldehyde, not by the ketone. So you can differentiate between the product of acid hydrolysis of P and Q easily by using the Fehling solution. Let's move on to our next question. Silver mirror test is given by which one of the following compounds? This question has been in AIEEE 2011. Options are acetaldehyde, acetone, diethyl ether, or benzophenol. You have some time to think about this question. After that, we will see the answer. Let's see. So the correct answer for the given question is option A, that is acetaldehyde. All aldehydes, including reducing sugars like glucose and fructose, give silver mirror test with Tollens reagent. RCHO plus 2 AgNH3 whole twice positive plus 3 OH negative, giving us RCO negative plus 2 Ag, that is silver mirror as a precipitate, plus 4 ammonia plus 2 H2, where in this reaction R is either hydrogen or methyl group. Thus, A, that is acetaldehyde, gives silver mirror test. As we said that aldehydes, including reducing sugar, give positive silver mirror test. And this is the one which we have to find out. So thus, our correct answer is option A, that is acetaldehyde. Okay. Thank you.